All right, everybody. So we'll start this evening's webinar on the topic of open source machines in construction. So let us take it away. So in the world of construction, you can do things with human labor, or you can use machines to facilitate that process. So we've done both, and I'll show you the experience that we had with both. But this is what we started with. When I moved out here, first structure we built was an earth bag hut. Then we made this cordwood hut. But let's look at some numbers behind that. Okay, cordwood hut, 6-week construction cycle. It was 1.5 people on average doing it, 150 square feet, $400 in materials. Super low cost. And then cost is low. That's a great advantage. It's super basic. I mean, you're just using dirt and twigs off the site to do it. For example, for the roof, we used black locust lumber, which is rot resistant and super hard. So it lives forever. So basically, carpet polyethylene soil theory on the top. It's dirt cheap. What we have is the wood, the black locust, lathing strips, which are rejects from a pallet mill in Jamestown, the Amish town. So we borrowed waste lumber from the Amish, put carpet, polyethylene, and soil on top. There you go. Oh, you can do it. It's you can do stuff dirt cheap like that. Won't necessarily be code approved, but if you get it engineered, you could build it in a city in principle, right? You just need an engineer's stamp. So then we start doing much more replicable standard stuff. The 5-day house with 60 people, 1,300 square feet. At that time, it was $30,000 in materials. The materials were low at that point. Right now, it's actually cost is more like $60,000. It's doubled since about a decade. But the figures, look at that. I mean, still, in terms of efficiency, actually quite similar. It was twice as efficient, like 0.2 person days per square foot, if you just look at the numbers. So the amount of person days it takes you to build each square foot of living space. So in 1 day, you've built 2 square feet, kind of deal. So look at this. It's 100 times more effective. 1/10 the time, 10 times more house. But the time per square foot is actually comparable. What's it say? It's effective. The time, you have to put labor into it, and no matter what the case. In a natural construction, it's like you just do it. You have to plan. You kind of just do it. Not a lot. You don't spend a lot of time thinking. You just spend a lot of time using your muscles. But what's the point of that? So
it's $23 a square foot. Like double that now, probably you're saying?
Yeah, if it was $23 a square foot for the actual, that's not counting labor.
Right.
So the materials cost would be, say, about $50 a square foot, just materials.
Yeah.
Now that's really good because in modern prices, that's decent. Well, so there's the time cost quality triangle. That's the golden triangle, so-called, and people say you can have 1 or 2, but not all of them. Pick 2 out of them. So if you have high cost, how does it work? Is anyone familiar with that? Can somebody explain?
High time, good quality.
Mm-hmm.
You can have 2. Yeah, you can have 2, but you can't have 3.
It's like the bikes,
Yeah.
where you can either have it be cheap and nice, but not tough, or you can have it be tough and cheap, but not
cheap and good, but it'll take a long time. You can have it fast and good, but it'll cost a lot.
Yep.
But high quality in a short amount of time, but it's going to cost a lot.
High cost, high quality. Hey, it's going to take you a lot of time. Yeah. All of those at the same time. So in initial vision, we talked about ecological housing that's off-grid, low-cost, collaborative, open-source, rapidly built, modular, distributed. we're effectively trying to say, how do you break that golden triangle? I think it's called the iron triangle. It's called the iron triangle because you can't break it. So we're asking, well, how can you collapse it? How can it be fast, cheap, good, all at the same time? So we like to integrate things. And a big part of that is machines, open materials that you can produce yourself. So in a Global Village construction set, and this is the materials facility, like the hangar will have some of this, but you've got things like sawmills, 3D printers, lime burners, CEB presses, and some machines like loaders, mixers, hammer mills, pelletizers, gasifiers that make all this happen. And into this you can also add induction furnace for steel, bioplastic extruder for 3D printing, for getting that 3D print material off from the waste stream, to make all kinds of things. Definitely lumber, compressed earth block, insulation. You can be talking about hempcrete or straw bales, like biomass fiber insulation. Take any biomass, straw, hay, hemp, mix some cement with it, and it becomes a solid thing. That's cement. That's actually what cement board is. Cement board is fiberglass with cement. You can embed various things.
Is it ash that they mix it with?
All kinds of formulas. You can go all over the place. But if you have some kind of a binder for biomass, now you've got insulation, and that's pretty cool. Or you can even aerate concrete. There's aerated concrete that you can produce that's insulative. For us, 3D printing, say multi-wall polycarbonate glazing, which would otherwise be really expensive. Yeah, you can 3D print that because polycarbonate, a transparent plastic, is a thermoplastic. You can melt it and reuse it and do it again. So the feedstocks are soil, limestone, so that's rock, hay, biomass, trees, and then for solar energy, primarily, if we use this from solar energy, the solar concrete concepts, the solar steel concepts, or hydrogen as fuel, they all come from the idea that you're just using solar as the energy source, solar electric as the source for running those processes. So instead of, for example, burning lime with natural gas, you're using heat from a resistive heater element powered by electricity. Or for steel making, that fuel source, it's not going to be, it's going to be electricity with an induction furnace. All right, so 2016, this was a big milestone where we showed the first time that we can do a structure like this in only 5 days. That's a good accomplishment. We didn't finish any of the inside and stuff like that. We just showed kind of like what you're seeing today. Today's structures, I would say it's actually a little more complex because of all the interior walls. Here it was a long structure with very few interior walls, but we did that in 5 days there. So those were the initial concepts. And what are all the machines in the set that help you do construction? Well, water well drilling rig, the tractor, the backhoe, the bulldozer, the trencher, the truck. Those are like mass handling machines. If we had them, we have done trenchers, we have done backhoe, we have done tractor. Well rig we didn't get far on. We don't have a truck or bulldozer yet, but in early stages of prototyping for the tractor, we've used it in the initial compressed earth block builds. We used our own tractors typically. Right now we're using skid steers for higher production rates as we're evolving the machines to completion. So the next step is absolute industrial grade on all the machines, and the next big deal is the open source skid steer, which we're looking at using 2 power cubes, each about 38 horsepower. So take 2 engines that are about 1,000 cc engines that are gasoline, 72 horsepower, industrial grade kind of a skid steer. That's our next game. That's kind of what I made the viral video about, the skid steer. And that's real. We know how to do that, and it's time to put in that whole bit of effort to get that to commercial production. As far as materials production, there's things like the compressed earth block press right here. The soil pulverizer is what we use to simply munch up the soil that we used in a compressed earth block and use that straight to press block. There's a haying machine. There's the bioplastic extruder. That's a hay rake. That's a baler. Sawmill, gasifier burner, pelletizer. So pellets are interesting in a sense that you see the effort with lumber. You got to take out the chainsaw and so forth. The pelletizer, I would say, is kind of the next generation of that, in the sense that you can have pellet wood stoves that if you feed them a whole bag, it's much easier. But how do you get all those pellets pelletize biomass? So you shred biomass and extrude pellets. So you can automate that. I mean, you just throw whole logs in there, you shred them, and then you press pellets out of that, and then you have a bulk fuel that's flowable. That means you can use it like gasoline. You can have a little hopper or a little auger that feeds that automatically, such as in a pellet stove. You dump the whole bag, it burns all day. You can then gasifier burner, charcoal that, so turn that into biochar by a process of partial combustion, so you can actually have fuel for a gasifier engine. We've built a gasifier engine, we fed it with charcoal. But I think actually a cool thing is with pellets, it's kind of a lower tech route where you have a flowable fuel that you can put into a fuel tank. You can dump a bunch of pellets that with a small auger they get fed into the engine and burned, such as gasified in the gasifier engine, if you're using pellets, turning them into charcoal, using that as a fuel. So engines could actually, you've heard about probably like wood engines that run on wood gas. This is a step above that, where you're not using wood, you're using charcoal, like coal, which is partially oxidized wood pellets. So it's interesting from that perspective, because it's an intermediate technology that you can use. All right. More things like 3D printer, cement mixer, hammer mill for shredding stuff. Mentioned the sawmill. So all kinds of machines in there for construction. So this is how we build. This is an example of, that's the dirt from beneath our feet. So that's straight from the CEB machine. We would press those block. You see that we call that microhouse 1. We call that microhouse 2. We connected them together and added to the back. That's the structure that has the aquaponic greenhouse that we formerly used. We're doing wood cladding. These are unstabilized blocks, so you got to protect them from moisture. What do you do? So that's, for example, our tractor soil pulverizer in action. We actually did mix a bit of cement in there and munched it up and threw that into the brick press to get stabilized bricks with not high quality controls. You know, some parts might have more cement, some parts might have less. You can probably recognize that smoke from all the cement, like we were burning it up last night. So that's what you do. Site preparation. Part of the site preparation can go into as a feedstock for your building, because if you're moving earth around, you've got piles of earth for CEB construction if you are doing CEBs. Stem walls, we've done that a lot, so that's another way to do a foundation. Yesterday we poured a whole slab, but you can just pour a beam on the outside. An effective way it could be to do this and fill the inside with crushed rock or fine gravel. You can get that and you can compact that to a very hard surface. That's actually what we're doing in the hangar. There's that fine gravel that packs down pretty hard if you compact it with a compactor. This is a way to do a pretty low cost, low embodied energy foundation, because there's a little bit of concrete on the edge, but most of it is just gravel. So it's 10 times less embodied energy for gravel compared to concrete. Now gravel isn't free, because there's a lot of energy that goes into actually breaking up that rock and transporting it in trucks to your site and all that. There's energy involved in that. Then we've done CEB walls. That's actually, we call that that was the build of the faculty house. That's the building actually that Elaine lives in. That's also a CEB building. You might not recognize it because it's clad with regular cladding, but that's what it is underneath. You see double walls which we put in cellulose insulation between the double walls. So we were using pretty much 100% natural materials there. Then we do things like structural modules like we are installing today, whether it's glazing or roof or wall modules. These are exterior walls. These here happen to be for the greenhouse. Stem walls, you can, in the same construction method, you can have sloped roofs very easily by raising one side over another. We tend to gravitate to flatter roofs so we can put PV right on top of that. We make roof modules. The roof modules that we installed on a hangar are quite big. These are human size. Basically, we built ones that were 3 by 16 feet as roof modules. You can do that. Right now we're going to the trusses that we're building, and then in this specific case we're lifting up the whole roof assembly with a telehandler using some mechanical assist. So yeah, top roof sections like this.
Are we holding questions to the end?
Yeah, let's hold questions to them. I'm going to wrap up pretty quickly here. Floors, we like hydronic heating in the floors. We have that here in other buildings. We have not done that as a standard feature in the house yet. We will come the thermal battery, like integrating the whole thermal storage cycle and cooling and geothermal, where you can run that hot or cold water in the pipes to get heating or cooling. I think that's good. Using water to a floor like this is super comfortable because you got that nice warmth coming from your feet, and it's really nice. Interior walls, exterior finishing. So a lot of the buildings we did were clad with some kind of a outside covering. But the thing is, here with open source machines and materials, you can try to smash the cost time quality triangle. If you talk about cost, if you have automated machines and high production machines, I mean, that definitely gets the cost and time down. If you have open source blueprints and then you have to have skills, then that really takes care of the quality. But if you start applying digital fabrication as well, I mean, you can address that. You don't have to have skill, you just have to hit print on your 3D printer or CNC sawmill to produce your materials or whatever you've got, so you can reduce the quality or the skill requirements required to attain high quality by both open blueprints, simple designs, things like measureless design and cutless design, or just simply automation where you're programming your robot slaves to do that for you instead of you being responsible for that. So you can get an assist from technology to help you build at high quality. And the cost, if you have access to machines that produce your materials, that is amazing. Like, in any build, equipment costs, the standard builds we do, the equipment is about 10% of the cost. There's a lot of stuff in the prep, such as the earthworks. You got to put in a lot of machine time to do that, such as site preparation, 2 days with mini excavator. You're finishing off the site, grading it, and making it all nice. I mean, you can do it all by hand. It's going to take you a long time, but you use a lot of machines. But that's the kind of cost structure we had. About 3,000 out of 30,000 was machines, and that's still just off-the-shelf materials. If you're building your own materials, then machines are going to be like 90% of the cost of your materials. So you can turn that cost from off the shelf to that which you invest into the machines, rapid, the effective production infrastructure through machines. Why local materials and local resources? Well, definitely there's a huge case. I mentioned that water heating, space heating, and cooling contribute to 70% of all global electricity use, including industrial. Think about that, it's huge. So you now if you get serious about solar panels, which are at zero marginal cost, and go solar, you're contributing to that. If we have access to things like the thermal batteries, which can store that heat when the sun is not shining. But otherwise, like if you're just reduced to solar without any kind of storage, I mean, that's only like 6 hours on average, so-called. Just nominally 6 hours of the day are full of sun. The rest, I mean, it's morning and night and no sun. So construction contributes to 35% of all carbon dioxide emissions worldwide. Transportation is 26% of all carbon dioxide emissions. So if you're doing stuff locally, that goes away or is reduced significantly. Lower embodied energy, such as compressed earth blocks, have 1/8 the embodied energy of fired bricks. I mean, that's significant. From the OSU perspective, like if we go into charcoal, and I don't talk a lot about charcoal these days because I think actually solar hydrogen is a much more robust solution. It's also higher tech, but it can power anything. It could be a complete substitute for all the kinds of different fuels that we use today. In fact, things like steel are actually improved. If you can do reduction of iron ore into steel using hydrogen, for example. So you can use hydrogen in many applications, including fuel and industry. Charcoal, if you go in an intermediate route, so like pelletizer and gasifier burner, where you're turning your pellets into charcoal as a flowable fuel. I mean, we haven't done that, so I'm not an authority to talk about it, but it's an idea that if you want to do that, charcoal could be a complete fuel replacement. It does not gum up your engine like the cars in World War II, which ran on wood. Over time, you would have tar buildup in the engine. It's just not robust because you end up destroying your engine after some time. Charcoal, if you use charcoal, that does not happen. Charcoal is pure carbon, and therefore you can burn it very cleanly, not like wood, which is going to have all kinds of other byproducts in addition, like such as tar that gums up your engine. But I'm just saying there are a lot of possibilities. So this gets into the biomass economy, which is fossil fuels is part of the biomass economy, except for millions of years ago, right? And once again, the big case for why this charcoal even makes sense, who knows? Here's a question for you to think about. How many days of solar energy coming to the sun did it take, if you have all the energy that the Earth intercepts, how many days equivalent of that energy did it take to make all the fossil fuels that ever existed or will exist? Does anyone know that number? What's your guess? How many days, years, or millennia?
100.
A million?
Years? Days? Million days?
No, 100.
Million days? That's high.
Sun hitting the entire Earth?
Yeah, like the amount of, because we talked about before, like one kilowatt per square meter comes to the sun. Plants use it up at a small percentage, like 1%. But there's a clue there. But in terms of the amount of energy that the Earth intercepts,
Like
the equivalent of that, what is the equivalent of all the fossil fuels in terms of the days of solar that come and are intercepted by the Earth?
Like if the whole Earth was covered with solar panels.
Yeah, I mean, I'm just saying the amount of raw solar energy, 1 kilowatt per square meter over the entire surface.
A month.
That's close. It's like 10 days.
Oh, wow.
I mean, Google this, study this. I think that's a very fundamental fact. I mean, nobody knows this, but just think about it. What does that mean? That means we're living in absolute scarcity in terms of our entire mindset and economy, right? 10 days. So if we tap what's out there already, we can. I think that can help shift our mindset to the real possibility of what's out there.
Yeah.
Study it. I mean, look at the actual underlying numbers, and I think it helps you make a case for why abundance can happen for everybody. Okay, so when we go out to work, we're going to create our construction trailer. We'll put all our machines on it and go to town. So you can think of doing the production sawmill that we transport to a site. Say we've got our full construction infrastructure up and all our machines. Bring over the CB press, lumber mill, and other goodies, and we'll just build from the dirt and twigs on any site. Yeah, let's do it. That's the general idea, right? I don't think that's. It's a high technological integration thing, but I mean all the technology out there exists to that. For you to do that right now, it would be pretty expensive if you're just using off-the-shelf materials. And the first thing you'll notice is that, oh yeah, one thing breaks, and then, you got to call the manufacturer, and they're like, oh, don't touch it, we'll be there next month. See you, sucker. And whatever. It's impossible to manage that with the existing technology set because it's too complicated and too proprietary, and you have too little control over it. When things break, you go broke. So that's kind of the reality. So if you can open source this, is the case for a robust capacity that you can ship anywhere to solve problems. It's part of the solving housing crisis. Can building materials be produced on demand? Yeah, why not? I mean, you can do on-demand compressed earth block. We've done that in all the houses. You have to address the issue that, yes, they will shrink a couple of percent. So, like, there's going to be like a settling of 1 or 2 inches at the top. So you have to design your top plate to basically drop with everything. Things like that. Lumber. Yeah, I mean, people can also build with green lumber. There's techniques to do that. If you're just cutting trees straight, or you put them in a kiln, and a week later, if you got a solar kiln, you can take the lumber out. Concrete, you can burn concrete on demand. If say we get a pile of gravel from the, I mean, in the future, in a few years perhaps, like within 3 years, if you come back, we'll do what we did with the pour, except we're burning our own rock in that same time too. We're going to spend a day. We're going to throw some rock into the kiln and get concrete out. We crush it and mix it with cement and rock, and there we go. We got our own stuff. All doable. 3D printer, yes, you can do that on demand. Steel, yes. 3D printing. Technology is not a question here. You can also produce materials on demand. Production rates, I mentioned before. Production rates are huge. For a sawmill, between $10,000 and $30,000 of lumber you can generate per day using commercial off-the-shelf sawmills. If open source, you can also control that over lifetime. Blah blah blah. CB press, 5,000 block in a day. Done it. It's insane. I mean, the production rate is huge. Initially, I was hoping for maybe like 3 bricks per minute with a first prototype. It turned out to be 10. I mean, engines and hydraulics, they work. Not a question. 3D printer. 3D printer rates are pretty slow, but you can have multiple heads on your printers, and each printer only costs about $300 in materials if you do it open source. So it's doable. You can put a lot of multiple printer heads, and you can actually get production level material production out of 3D printers. If you have bigger nozzles and little higher power nozzles, heater elements in your 3D printer, it's doable. Construction trailer 2.0 include induction furnace, melt steel on demand. Fab wagon, the mobile open source solar powered microfactory. Yeah, sure. 3.0. Oh yeah, we could do, so the aluminum extraction from clay is actually one of the technologies in the Global Village construction set. What's clay? It's aluminosilicate, AlSiO. Aluminum, silicon, oxygen, that's clay. There's plenty of oxygen, silicon, aluminum, iron, and rocks. Aluminum extraction from clay is a concept where clay is everywhere. So it's dedicated to show that if you can actually show this, that's cool. You can say, okay, wow, metals from dirt and rocks. Good idea. We haven't gotten there yet. It's doable. Conclusion. Yeah, I mean, you can reduce your impact and become fully environmentally friendly. You can do the raw materials without much automation or mechanization, and it'll take you time. It'll be low cost, but then you can also use open source techniques and machines to get industrial grade productivity on a small scale for the next abundance economy. So I'll leave it at that and open it up to questions. Any questions also from the audience? And no.
Martin,
Go
I've
ahead.
seen someone recently, younger guy. He's got solar powered device that's taking plastic and turning that into fuels.
Oh yeah.
Gas. Have you seen that?
Have seen it. That's great because plastics are pyrolysis. Plastic pyrolysis, and basically plastic is fuel in disguise. So to get diesel or gasoline from it is a pretty simple device, and it's actually, we should do that as soon as possible because fuel is a huge cost in our operations.
Yeah.
Yeah, that's legit. It's all good. just open source that design fully and make it
Yeah.
beyond, like, say that whoever did that. I mean, I'm not sure what level of refinement it is, but I mean,
He's gotten it down to like really high octane levels, and he's running in cars and like high octane vehicles. And,
Ben, you're talking about the
Diesel
guy who did
and-
microwave pyrolysis?
Yeah, I think so. Yeah.
Yeah, that's
Nature
Forget his
guy?
name.
yeah.
He's running
that's,
it all off of solar panels.
You don't want to mess with that unless you're like really, really good at it. He almost killed himself a couple of times doing that.
Yeah.
from what, like stuff where liquid fuel
He's
dangers.
just a high-powered microwave. What's it called? No, I'm forgetting. I'm forgetting the name of it. But basically, he had a couple of nasty explosions
Yeah.
when he was going through that.
Yeah, you gotta watch out for that, naturally. But once again, once you get it to a refinement high enough, you put in those safety features, and that's the part where you're talking about productizing and getting it through all the safety checks and approvals from authorities, which is legit. There's bodies that check that you're not gonna blow yourself up, and in that case, that's good. If you're producing open source blueprints, you have to do that. So for us, it would be that we actually go through whatever it is, CE or UL listed, whatever, all the standards organizations, you tap into that and they approve it and you get certified to do that. But we just open up the standards so anyone can replicate it. Yeah, that's the idea. And regarding that plastic pyrolysis thing, I mean, is that, first of all, my initial question is it open source? Is he open sourcing all the designs?
I don't remember him saying.
No, he's productizing that. He's patenting all that stuff.
So that's what we're running into. Yes, cool, but that ain't gonna change
He's
the
getting
world.
sponsors. Like, his mom was like,
Yeah. I believe any civilization reconstruction effort has to start with education, and if you're talking about proprietary, that's not compatible with education.
yeah.
Because you're not sharing your stuff. You're not going to teach anybody else how to do the real stuff. You'll give droppings off the table, give people the breadcrumbs, but you're keeping the bread. You know, so that's the issue with that. Other questions? Bo?
Yeah, my original question was just, what about the solar panels that kind of tilt to keep facing the sun? Did you ever?
Yeah, you can do that absolutely, but if you do the cost analysis on it, the tracking mechanism can add up to price so much that because solar panels are so inexpensive right now, it doesn't really matter. I think people used to pay a lot more attention to that when solar panels were like 10 or 100 times more expensive, in which case it does make sense to do that. But right now it doesn't make sense financially. Yeah.
What's the square footage of the solar panels that you're getting the 6 kilowatt hours out of?
Square footage is going to be about 600, what is it? Each one, there's 27 times about 3 by 6 feet. Like, so what is it, like 900 square feet? No, that sounds too high. We have a roof and the panels, okay, I can tell you the comparison. If you look at the overhead shot, we know the footprint is 720 square feet, which is what we have in the workshop right now, which, by the way, looks much bigger than, it looks pretty big. Solar panels are most of that space, so probably like 500, 600 square feet for that, which about is right, because 10 square feet, if it's about, say, nominally 10% efficient, if you got 600 square feet or 60 square meters, that's about 6 kilowatts at 10% efficiency, nominally, yeah. So about 600 square feet.
Are we going to cover the thermal battery? Did you say this?
Yeah, we're gonna cover that.
Oh, okay.
We want to make sure we have a day for that. Any other thoughts?
Oh, what's the advantages of the induction furnace for melting scrap?
Induction furnace is the most energy efficient way to get energy directly into melting steel. You can do flame stuff or resistive heating, but induction is the way it works. It resonates with the metal itself. It doesn't, so it heats up the metal mass, not like flames, which heat up everything. It's kind of selective, so it's actually highly efficient. You can get pretty good efficiencies.
Using like an RF frequency to heat the metals?
It's a high frequency power source induction.
It's electromagnetic, right?
Yeah,
Yeah.
electromagnetic radiation.
They turn on and then like the middle starts heating up.
Right.
Yeah.
Only work for.
Yeah, it's oscillating electricity going through a copper coil that the actual,
Like induction cooktops only ferrous metals, so
yeah, it's same thing. Induction furnace,
you wouldn't be able to melt say
Induction.
aluminum in an induction furnace, could you?
you can.
Okay.
It's because
Why
the
not?
other metals are heating the aluminum.
Oh, if you have to have a crucible that
Okay.
is conductive.
Okay.
Yeah, I think that's how they do glass. But with glass, it seems. I think the way it works with glass actually becomes conductive once it melts. So first you got to heat it up, and then you can do induction on the melted thing, which actually conducts. Liquid glass, if I'm not wrong, I think
that's
that's
right.
yeah. But yeah, induction. Yeah, because you're saying, well, how do you heat something that's not a metal, which doesn't conduct? Because electromagnetic radiation only interacts with metals, things that have free electrons. But yeah, if you have a pot, a chamber, like on your cooktop, you can heat water with it, but you're actually heating the metal pot, not the water, and the water takes up the energy. Yeah. Mm-hmm. All right. One more?
We still start at noon tomorrow?
Yes, yes. So thank you for the call. We're going to wrap up here. I'm going to quit the recording. So on site, I think so.